Okay, Antoine, whenever you're ready, and whenever you want to start, it's fine.
Okay. So let me continue on what I was doing yesterday. So I was trying to talk about nilpotent manifold and N structures. Maybe briefly, I should recall a little bit of what we did last time. Recall that last time we said a lot, I think, about F structures, and you can think of F structures as local torus actions. Actions that are glued together, that are somehow compatible. And
quitte à avoir peut-être d'autres moments où ils peuvent présenter ça justement à des chercheurs.
Tu dois couper son micro. Diaraf, il faut couper ton micro.
And so that's about F structures. And today we're going to see N structures where essentially we just replace the torus actions by nilpotent groups. Okay. Yeah, so for F structures, you had existence. And once you had existence, you had those collapsing constructions. And today we'll see something very similar for N structures. So we'll at least state a result about the existence and also see something, a corresponding collapsing construction. No worries. Right, so another thing was this example of nilpotent collapsing, where you just take the Heisenberg group and you take a nice metric and you realize that the metric is collapsing, even though your manifold cannot be flat. And so that calls for something more than F structures, right? And I mentioned that quite remarkably. So you have the converse, meaning any almost flat manifold is given essentially by a nil manifold. I'm going to restate that there. So I'm going to continue from here. Oh, yes. So maybe I can. So what's the result? I guess. Say that M is almost flat. If there exists a sequence of metrics on M with fractional curvature bounded, then the diameter goes to 0. So it's a very strong kind of collapse. And say that say M prime is a nil manifold if M prime is diffeomorphic to a quotient of a nilpotent Lie group. Nilpotent Lie group, meaning that if you take commutators of your Lie group and you continue, eventually you get to the trivial group. And gamma is a co-compact lattice inside N. compact lattice. So right. Now the statement of Gromov's theorem is that almost flat manifolds are exactly those which are finitely covered by a Néel manifold. There's some detail here, but so any almost flat manifold is diffeomorphic to a finite quotient of a Néel manifold. And what's strong about that theorem is that it gives you the diffeomorphism type, and also you have no hope of proving such a theorem by just a blow-up argument, because again, of all those different scales that can collapse very differently. So this is one of the keystones of this theory of n structures. Let's see what we can say about that. Oh, yes. Let me share the Jamboard link for today. I think it works today. Yes, one remark is that, let's see, what kind of remark do I want to do? Okay, I don't want to talk about the proof of this theorem, but there's a reference. There's this text of Boozer and Karcher, and the Boozer and Karcher essentially gives a detailed proof of Gromov's theorem, and it's very well written, so that's really nice. That's my first remark. The second remark is that you have a powerful generalization of this theorem, especially in the case of lower bound on Ricci. But these are generalizations on the level of the fundamental group. You cannot really get something on the smooth structure. However, you do get something on the fundamental group of almost flat manifold when you replace sectional curvature by lower bound on the Ricci curvature of I1. And so for that, we can look at Kepler Filtering, for example. And for those who read French, there is a survey by Courtois, Gilles Courtois. Right. Gromov's theorem can be generalized, and this is what Fukaya did. And this is where Fukaya enters into the story. Let me give you this generalization by Fukaya. It's a kind of parametrized version of Gromov's theorem. To a parametrized version. So Fukaya wrote a few papers by himself, so 87, 88, and 89. And in one of them, he proves the following generalization. If you have that manifold of dimension n and another smooth manifold of dimension, say m, so these are two Riemannian manifolds. and the sectional curvature of your first metric is less than 1. And the Gromov-Hausdorff distance between M and your second manifold is very small. Smaller than a dimensional constant. Then there exists a vibration map Z with Z of dimension n minus m. So you have this map from your n-dimensional manifold to this new manifold Y, and the fiber is an almost flat manifold. Is an almost flat manifold. So in particular, this fiber by Gromov, it's a finite quotient of a Néel manifold. Néel manifold. In fact, Fukaya kind of reproves that he cannot directly apply Gromov's theorem. But for us, it doesn't matter. What matters is that you have this vibration theorem, and it's a parametrized version of Gromov, because if you take this base manifold to be a point, you exactly recover the statement of Gromov's theorem, right? But now you have somehow a continuous family of such almost flat manifolds that are parametrized by a base manifold Y. So this is nice. This is a generalization of Gromov's, but at first glance, it seems that it's just a generalization. It's a little bit hard to use, because it seems that the condition that the Gromov-Hausdorff limit is a manifold Y, that's hard to get. That's hard to satisfy, right? And but in fact, we'll see that it's completely general, and that's really nice. So let me write down that remark, which is, you might hope to say, well, now you take a sequence of metrics with bounded sectional curvature, and you want to take Gromov-Hausdorff limit. You hope to get a manifold, you would be applied to this theorem, you would be happy, you go back home. But that's not possible, because if you take a sequence of metrics with sectional curvature bounded, you can always take a pointed Gromov-Hausdorff limit, that's fine. And you get the space, XD. But in general, D is pretty far from being a manifold. It doesn't even need to be an orbifold. Doesn't need to be an orbifold. So that's sad, but in fact, you still have quite a lot of structure. It's not just a random X that you get. In fact, locally, X can be written as a nice quotient of a piece of Euclidean space by a Lie group of transformations. So near any point in your space, in your limit, there's an open set. Say there's a U open set that contains your point, such that U is in fact homeomorphic to a quotient V by G. So what is V, what is G? Here V is a neighborhood of 0 in the Euclidean space. So in Euclidean space, so here of dimension, the dimension of M. And G is a group, Lie group of transformations. Of transformations of V. And in fact, the intuition is not so hard. So let me give you the intuition behind that statement. If you take, say, sequence of open sets in MGI, somehow converging to this open set in X, a small open set in X, and you look at the universal cover of UI. The universal cover. Remember that UI has this metric GI, a bounded sectional curvature, so you lift everything to the universal cover. You get an induced metric, a lifted metric, GI tilde with a bounded sectional curvature, but now the injectivity radius of the universal cover is uniformly lower bounded. That's really good. Activity is lower bounded by a constant, not depending on I. So you can just imagine that UI tilde with its metric is very close to being the flat, a flat open set in Euclidean space. Now you consider the local fundamental group around these points. So consider the fundamental group of UI. And let's call that GI. So GI naturally acts by isometries on this universal cover UI, tilde. UI tilde. And so now the idea is just, okay, take a limit of these groups GI, you should get something. Of those group GI. And you should get a limit that we'll call G. In fact, in order to say that, you look at elements of your groups as Lipschitz transformation of, say, the Euclidean space. And by compactness theorems, you can get always a limit, something which is a limit. And then you prove step by step, it is a group, it is a Lie group, things like this. Use Arzela Ascoli or something similar to that, so that you can get G, a set of transformation, and then you show that it's a Lie group. He is, in fact, a Lie group, and V is somehow the limits of the universal covers, so that at the end of the day, you do have that U is a piece of Euclidean space divided by a quotiented by a Lie group of transformations. Quick example. So if Z acts on R2 by translation, for example, it sends X to X plus, say, K times eta times E, where E is a vector in R2 and eta is a small number. So you see that when eta is going to 0, this group action and this group Z, they are converging to an action of R. Okay. As eta goes to 0, Z in the sense above converges to R. This is essentially what we're doing here. Right, so this remark was just to say, your limit, the Gromov-Hausdorff limit upon the sectional curvature, still has some structure. It is a Euclidean space quotiented by a Lie group. And now the question is, all right, but how do you apply the fibration theorem of Fukaya? Because in the fibration theorem, really the assumption is that the Gromov-Hausdorff limit is a smooth manifold. So how to apply the fibration theorem of Fukaya. And here there's a very nice idea of Fukaya, which is look at the orthonormal frame bundle. Look at the orthonormal frame bundle. So the things are messy in the original manifold, but if you lift everything to the frame bundle, suddenly everything is clear. That's what I want to explain next. First, I'm going to recall some basic fact about the frame bundle. Just very quickly, recall that if you're given a manifold with bounded sectional curvature, you can define the orthonormal frame bundle that I'm going to denote by FM. And sometimes I'm just going to say frame bundle, but I really mean orthogonal frame bundle. And it's the bundle of, so as its name indicates, orthonormal basis at every point. And this is an ON principal bundle. So the fibers, this is a bundle. Each fiber has a group structure, an ON structure, the orthogonal group. So this is an ON principal bundle. And moreover, so the metric on M lifts in a natural way to a metric on FM. That you lift using the Levi-Civita connection. And this lift makes the projection a Riemannian submersion, so that it's a Riemannian submersion. Here the ON fibers are sent to points, no? M. One thing, ON acts by, of course, isometries on this metric, since everything is natural. And you have an ON principal bundle. Acts by isometries on FM. And moreover, the sectional curvature of this new metric, this lifted metric, is also bounded by a dimensional constant. So that means now if you have a sequence of metrics with bounded sectional curvature, the idea is look at everything that's lifted to the frame bundle. You have a new sequence of manifolds with bounded sectional curvature. We can look at Gromov-Hausdorff limits of these guys. And the claim is that Gromov-Hausdorff limits of these guys are manifolds. And then you can just apply the vibration theorem of Fukaya to get some structure. That's the plan. So I'm going to revise our the previous remark. Let's see. So you can MP as usual. We'll suppose that we'll suppose that these metrics GI are called regular. Well, suppose A regular, meaning for all j, say, the norm of the jth derivative of your metric computed with itself, the metric itself, that's controlled by a constant A j. So A denotes the sequence of AJ. And that's not a strong assumption, meaning, okay, if you start with a metric of bounded sectional curvature, what you can do is you run, say, the Ricci flow. That's one way. There's maybe more pedestrian ways. You can smooth out your metric so that it becomes a regular metric in that sense, where A only depends on your dimension. It's a sequence of positive numbers only depending on your dimension. You look at the Gromov-Hausdorff limit of these metrics. And I'm going to call this metric space X hat. So by definition, is the point at Gromov-Hausdorff limit of the frame bundle with the lifted metric. Okay, you take a sequence of points, with points. And the claim is that this is a smooth manifold and the hat is a smooth metric. And once you have the idea of looking at the frame bundle, at least the intuition behind that fact is not so mysterious. So let me explain that non-rigorously, as usual. So you have the frame bundle, you have this natural projection by I to your base manifold. And so you know that you have convergence to some limit spaces. Okay, this arrow is not a projection, and it might be confusing, but I'm saying here that the arrow is just for the convergence. converges to a limit space. And in fact, you have an induced kind of projection, a map. Here, remember that on Fm, you have an ON action, and that goes to the limit in a natural way. So on the limit, you have an isometric action on x hat. My symmetries. And this guy is given by taking a quotient. So let's see. If you take the quotient of your limit space x hat by this isometric action by ON, you get exactly the Gromov-Hausdorff limit of your original sequence. And by the previous remark, you know that X is locally a quotient. So by previous remark, X is locally at least homeomorphic to a quotient V over G. So in fact, here you can repeat this argument and you get that locally X hat is also such a quotient. But now the key remark is that G, this group of transformation, is coming from isometries of MGI. So that means these isometries, they lift to the frame bundle, but it is a well-known fact that a non-trivial isometry of the base space lifts to an isometry of the frame bundle without fixed points. Whenever you're non-trivial isometry, you cannot have a fixed point in for the lift in the frame bundle. So this limit group comes from isometries of your manifold, at least, yeah, logo universe cover, but and then so that's the key remark. Non-trivial isometries of this guy lift to isometries of the frame bundle that has no fixed point. Without fixed point. So if you have a group of isometries acting on a manifold again, if you lift this group of isometries to the frame bundle, you get a free action. So here, G acts freely on this piece of Euclidean space V hat. So by the slice theorem, the quotient is a manifold. It's freely on V hat, which I remind you is a kind of limit of these local so frame bundle of universal cover. Right? So when you take a quotient by such a free action by a Lie group, you get a manifold by the slice theorem. And all that means is that now you can apply this vibration theorem of Fukaya. So while at first sight, the vibration theorem was asking for a lot of assumptions. In fact, these assumptions are always met when you take the frame bundle. Vibration theorem of Fukaya. So this is what Fukaya did. And later, Cheeger, Fukaya, and Gromov put everything together, formalized a little bit everything to get something called N structures. Cheeger, Fukaya, and Gromov in the paper of 92. They combine this idea and they get an equivariant statement that goes as follows. These ideas get an ON equivariant statement as follows. There exists a dimensional constant delta n and rho n, and given a manifold with bounded sectional curvature, suppose that G is irregular. Again, that's not very constraining. If the injectivity radius is smaller than this dimensional constant delta n, then around any point, for any point in M, there exists a certain space, a certain manifold, Riemannian manifold, YH. There exists a U, which is a neighborhood of X that is big, uniformly big, in the sense that it's containing the ball centered at X and of radius rho. Such that you have the following. So first thing, you have a nice vibration map. Vibration. Oh, let me change page. Okay, let's recall the notation here. Y is a Riemannian manifold, U is a neighborhood that is uniformly large. What do you get? First, of course, you have this vibration map. Boom, boom, boom. So F is the vibration map to this Riemannian manifold Y. Moreover, Z, the fiber, is diffeomorphic to a Néel manifold. Actually, you don't even need to take a further finite quotient. You just get a Néel manifold, meaning a simply connected Lie group divided by a lattice inside N. That's a fact. Moreover, the vibration map is ON invariant. Invariant. And moreover, you can talk about being close to a Riemannian submersion. And F, this vibration map, is close to being a Riemannian submersion. And moreover, it is B regular for B that depends only on the dimension and the regularity that you imposed in the beginning for G. So what this theorem means is that for any manifold with bounded sectional curvature on a definite scale rho n, you can get this structure that comes directly from looking at the frame bundle, applying Fukaya's vibration theorem, right? And yes, so here there's this fact that the fibers, they're almost flat, but they're even better. They're simply Néel manifolds. That also comes from the fact that in the frame bundle, things are much better, much easier. So that's the main, I think, one of the main ideas of having a good structure theory for n structures, which is this observation to go to the frame bundle.
Antoine, there is a question in the room.
Yes.
Yes, in the previous slide, why the limit of G acts freely on the limit space?
Your question is why the limit should act freely, is that right?
Yes.
So let's see. I think whenever you take a non-trivial transformation in this G, it will act freely because, again, this G is a limit of transformation of the frame bundle, and which are lifts of transformation of a base space. And again, lift of those isometries are free isometries, meaning they don't fix any points. Whenever they're non-trivial, they don't fix any point, right? So if you take a limit of such transformation, you get a group. This is a claim, and it acts freely. This is another claim, because this group is a limit of element acting freely on frame bundles. Does it answer the question?
I have still some doubt, but it's okay.
Right. Maybe I'll come back to that later.
Okay, thank you. We will talk later.
Yes. All right. So let's suppose we believe that. Then you have all of this, and now we're going to take this term as our definition of being an elementary n structure, having an elementary n structure. So it's not exactly the definition of n structure that Cheeger and Fukaya Gromov are using, because they're mainly using the original manifold M. But for simplicity, and because it's essentially completely equivalent, I'm going to talk about n structures as something defined using the frame bundle. So what we can do is to take this property and make it as a definition for being an elementary n structure. N structure on, say, the open set U, this neighborhood of X that contains a ball of definite size. And it's very similar to F structures. So F structures, it's a bunch of elementary F structures that you define on open sets, and then you glue these F structures together. Similarly, an N structure is going to be defined as a bunch of open sets on which, on each open set, you have such an elementary N structure, and they glue together in a nice way. I'm going to give no formal definition for the general N structure, but let me say that an N structure is defined as a finite numbers of elementary and structures that are defined on some open sets. U alpha is an open cover of M, and you have some certain compatibility conditions on the intersection. You want the Néel manifold fibers to be contained in one another, or vice versa. Compatibility conditions on intersections of U alpha. Right, so an elementary N structure is just, you look at the frame bundle, you have this fibration with fiber Néel manifold. And the main theorem of today is going to say, similar to F structures, whenever you have a bounded sectional curvature and you're collapsed enough, you actually carry an N structure. That's the statement of Cheeger, Fukaya, Gromov. For all epsilon, there exists some thresholds that depend on this epsilon, but mainly on the dimension, such that if your manifold has bounded sectional curvature and the injectivity radius of G is smaller than this threshold, then there exists a new metric, and this new metric is very close to G. It's epsilon close to G. Moreover, G epsilon is invariant for the N structure. For, I should say, one N structure. So there exists an N structure. And this N structure is defined on uniformly lower bounded sets. So a uniform size is defined using open sets alpha for any point in M. The ball of radius rho n is included in one of those open sets U alpha for some alpha. You have finitely many of those U alphas. The important point is that contrary to F structures, N structures are saying something on the scale of 1 essentially. So this rho n is only depending on the dimension, okay, also on epsilon. But the N structure is living on that scale. This is the macroscopic scale. Here, another remark is that what do I mean by being invariant? It's not clear what the action is. All right, so if you look at an elementary N structure, you have this fibration map with fibers which are Néel manifold. So on Néel manifold, you naturally have a so-called invariant metric. And what I mean by G epsilon being invariant is that if you look at a metric restricted to these fibers, you actually get a metric that is invariant in that sense. The n structures of the theorem live at a macroscopic scale. Yes, so that is the main advantage compared to F structures. Let's see, so this theorem, or the proof of this theorem, is going to imply a lot of nice properties of the n structures. So I'm going to make a list of those important properties. The structures. So these properties are either following from the statement itself or the proof of the statement. The first property is that in the same way that, say, an F structure divides up your manifold into a disjoint union of orbits, an N structure is going to divide up your manifold also in a disjoint union of orbits. So, and the orbits now are going to be quotients of nil manifolds. That implies that the frame bundle is a union of so-called n orbits, which are those fibers, remember, those fibers which are of the form being a nilpotent manifold, just a quotient of a simply connected nilpotent ring group. That's in the frame bundle, but you can quotient by ON and get back to your original manifold. And so these n orbits project to things that are still called orbits inside M. So M is partitioned into this disjoint union of orbits. The form. So each orbit is of the form a finite quotient of a nil manifold. So. In fact, each orbit is diffeomorphic to an almost flat manifold. So that's the first thing. The second thing is, what is the second thing that I would like to say? Yes, so recall F structures are defined using some torus actions. Defined using torus actions. So an elementary F structure is simply there exists an effective torus action in a finite normal covering. So here you can use the same kind of action language. You can find a covering of a normal covering of open sets of your frame bundle on which a nilpotent manifold is going to act effectively and smoothly. there exists U, there exists, so you take the universal cover here, on which a nilpotent Lie group is acting not exactly effectively, but with discrete kernel. It's a smooth action, and which is almost effective in that sense. You see that this way of saying things is very close to the definition of F structures. Third remark, what is the link, a more precise link between F structures and N structures? My third remark is to say that given an N structure, as in the theorem, you get automatically an F structure that induces an F structure. So where is this F structure? How do you see it? Well, you look at the N structure in the theorem, and around each point in the frame bundle, you have this fiber, which is a quotient of N, right? N is a simply connected nilpotent Lie group. You can look at its center. And the slogan is to say that if you take the center of this N structure, you get an F structure. So the center is a non-trivial abelian space, and if you quotient the center by this gamma, you get a torus, what I'm going to call T. Now, the projected orbits of this N structure contains, of course, the projection of these tori. Contains the projections of those tori T. We get a quotient of a torus, and it follows from the proof that you're quotienting by a subtorus extension of finite groups. So what you get is not a torus, but a flat manifold, a finite quotient of a torus. Flat manifold T prime. And there's another claim that you need to check, which is that this final quotient is always of positive dimension. These quotient of tori, so these flat manifolds, are forming the orbits of an F structure. And have structure of positive rank. So I hope that the geometric picture is clear. Whenever you have an N structure, it's something defined on the frame bundle, but on the frame bundle, locally, you can take a universal cover, you get a nilpotent Lie group acting on it. Now, if you restrict to the center of this nilpotent Lie group, you get an action by an abelian group. You look at the orbits of this abelian group, that gives you some tori in the frame bundle. And actually, if you descend to the base manifold, you get some flat manifolds. And these flat manifolds are exactly the orbits of a certain F structure. The F structure comes exactly from this torus action or Rn action, or K action that you had in the, say, frame bundle. So this is the link between N structure and F structure. Automatically, an N structure that is given by the theorem contains an F structure of positive rank. So the positive rank here comes from the fact that you're really looking at the N structure of the theorem. That's a technical detail, but in general, given a general N structure, you can always, by taking the center, get an F structure, but maybe it's not of positive rank. So why is it of positive rank here? It's because it's an N structure coming from a collapsed manifold. So that is a satisfying generalization of F structures, right? Because you have this nice structure that describes things on scale 1, and that gives you back the previous structure, F structures of positive ranks. And last remark, which is the last property that I want to talk about today, which is to have a very nice picture of what such a manifold looks like. So if you take any point in M, you endow M with this invariant metric G epsilon that comes from the theorem of Cheeger, Fukaya, Gromov. Remember that G epsilon is very close, epsilon close to your original metric, but G epsilon is somehow invariant for the N structure. So any point is contained in a neighborhood of the form or a tubular neighborhood of Q, where Q is an orbit, a projected orbit of the N structure. And I remind you that such an orbit is always diffeomorphic to a finite quotient of a nil manifold. It's an almost flat manifold. Manifold. And moreover, R only depends on the dimension and epsilon. So what it means is that you have a fixed scale on which you can really exactly say what you look like. The manifold, on a fixed scale, the manifold is simply an R tubular neighborhood of an almost flat manifold. And the metric on this tubular neighborhood is uniformly close to the natural metric that you would put on such a normal bundle of Q. So Q has its own metric, and the tubular neighborhood is a normal bundle, so it has a natural metric on it. And I'm saying that this neighborhood with the metric G epsilon is very close to this normal bundle, this neighborhood with the normal bundle metric that you would put. You can compare this statement to the situation with F structures, where we had to say we start with a manifold of bounded sectional curvature. We had to blow up the metric, rescale the metric until the injectivity radius is bounded in order to see a complete flat manifold, which is nothing else than the normal bundle of a compact flat manifold. And here, you don't need to blow up the metric. You don't need to rescale it. What replaces the flat manifold is going to be this finite quotient of a nil manifold, an almost flat manifold. So that's it for N structures. And I'm going to end this lecture by talking about some applications. first you have some other kinds of collapsing constructions. And you also have other applications. Whenever you have an F structure of positive rank, you can construct a family of metrics collapsing. And so now that you have N structures, there's many ways you can try to generalize that collapsing construction. And I'm going to give you one possible way to generalize this construction using N structures. And for me, the key point is that N structures have uniform control that the F structures found by Cheeger Gromov do not. So those N structures found by Cheeger, Fukaya, Gromov, they induce naturally a canonical F structure, as I tried to explain. You just take the quote unquote center of your N structure. But the N structures, again, found in this theorem of Cheeger, Fukaya, Gromov, they have, by construction, some uniform control because they come from this map, this vibration map of Fukaya. And the vibration map of Fukaya has some very nice uniform control. So the induced canonical F structure also enjoys these uniform controls. So uniformly controlled. And what does it mean? Well, you want to improve, and now I'm going to give a statement. You want to improve the collapsing construction of Cheeger Gromov. And the idea, so the proof is not easy, but the idea is simple. You want to kind of apply this construction of Cheeger Gromov I explained in the second lecture and third lecture, so that you want to apply this construction to a special F structure, the one that you get from this N structure. But because the N structure has uniform control, the F structure too, and so you will get some bounds that are more uniform in the sense that follows. By applying the collapsing construction of Cheeger Gromov, so we apply this to that canonical F structure. One gets the following improvement. So if the sectional curvature is less than 1 and the injectivity radius is less than a threshold that depends only on the dimension, and if G is a regular metric for some sequence of positive numbers A, then you have the same statement as Cheeger Gromov. So T is between 0 and 1. G1, so you start at the metric G. And moreover, you have two things happening. You have collapsing. So you have two things. This is going to 0. The sectional curvature is uniformly bounded, independent of T. So you might ask, yeah, well, okay, so what's improved here exactly? It's the dependence of this constant on your metric. these constants now are not depending on the particular metric you choose, just the degree of smoothness that you impose on them. And remember that the smoothness is not something too expensive, because you can just smooth your metric using, say, the Ricci flow. You get a certain A here. And similarly, the rate, the speed at which this injectivity radius goes to 0 is depending only on N and A. On N and A. So the conclusion is that you have this collapsing construction, and it is improved compared to Cheeger Gromov, simply in the sense that the constants that you get are depending not on the metric you're collapsing, not on the special geometry that you're collapsing, only on the dimension and the regularity of the metric. So that's the technical consequence, one of the technical consequences of this theory of N structures. And it has some numbers of concrete applications that I want to mention now. Remark or local versions of that improved collapsing construction, meaning that local in the sense that you have maybe a non-compact manifold with bounded sectional curvature, and you just want to collapse a part, a compact region of your manifold. So and you can do that with a uniform bound on the sectional curvature depending only on N and A, similarly to the previous statement. So now let's get to some more concrete applications that are involving, say, the minimal volume or the essential minimal volume. So first application is that, remember, so recall that we have defined minimal volume and also essential minimal volume. And recall that the essential minimal volume, contrarily to the minimal volume, is by design always achieved by the volume of some manifold in a weak closure of the set of metrics with bounded sectional curvature. And there exists in the weak closure of the space of bounded sectional curvature metrics on M, you have this complete Riemannian manifold M infinity with a metric C1 alpha metric G infinity, such that the essential minimal volume of M is simply the volume of this manifold. And M infinity is obtained by M by discarding some collapsed regions. So regions covered by F structures or N structures, if you want. So now my first application is going to say, for any M, so closed manifold M and M infinity as above, achieving the essential minimal volume, the number of connected component of M infinity is finite. So, M infinity is finite. In fact, M infinity cannot have delta N collapsed connected component, in the sense that it cannot have a component where everywhere the injectivity radius is small, because you apply local version of the improved collapsing construction. By applying such a local version of the improved collapsing construction, you can prove that such components in the limit m infinity cannot exist, because you would be able to collapse them to the empty set, but that would contradict the definition of essential minimal volume, which is taking an infimum, right? And one needs to be careful here. The theory of F structures and the construction of Cheeger Gromov is really not enough in order to do that. It's a bit counterintuitive, but when you try to argue and write down the proofs, you realize that you need some uniform estimates, and those uniform estimates come from N structures and this improved collapsing construction. That's the first thing you can say, immediate thing you can say about the essential minimal volume once you know about N structures. The second thing is a comparison between different kinds of minimal volumes. And what you can say is there's many ways of defining a minimal volume, right? You just, for example, you can impose simply a lower bound of the sectional curvature. And so that is a smaller minimal volume than the usual standard minimal volume, where you impose a sectional curvature bound pointwise in lower bound and upper bound. But the application here is that you can estimate this in terms of the essential minimal volume, and that is non-trivial. The trivial part is that this is always less than the standard minimal volume, since the standard minimal volume is about a stronger curvature condition. And how do you do that? So let's imagine what's happening for the essential minimal volume. It is the volume of M infinity, and but M infinity might not be diffeomorphic to M. You need to remove some regions of M to get M infinity, but these regions are covered by N structures, so we can again apply a local collapsing construction that is adapted to this situation. I don't have time to explain why, but really the key is to apply a variation of the local collapsing construction. The improved local collapsing construction. So immediately from this, we can talk about hyperbolic manifold. So remember that Jarabesson, Protois, and Silvestre Gallo, what they proved was that for any hyperbolic manifold closed of dimension n, the infimum, what they prove is much more powerful than what I stated on the first day. What they prove is that if you look at this minimal volume, this is equal to the volume of the hyperbolic manifold with the hyperbolic metric. So as a corollary of that, so this is what they proved. As a corollary, of course, first you have immediately that the minimal volume of your manifold is the hyperbolic volume, but you also get, because of this B, okay, point B, you have that the essential minimal volume is also equal to the hyperbolic volume. And I don't know how to prove such a statement if you replace in the definition of essential minimal volume a Ricci lower bound instead of a bound on the sectional curvature. And finally, a last application, which is to compare the essential minimal volume to the minimal volume. We saw that in dimensions higher than 4, in general, the two can be arbitrarily different. It's a little bit strange, but essential minimal volume can be arbitrarily smaller than the minimal volume. However, in low dimension, So in dimension 2 and 3, they're equal. Is equal to the minimal volume. In dimension 2, it's a direct computation, nothing difficult, but in dimension 3, you need to prove something. And you need, in fact, to use the fact that in dimension 3, it is known. Okay, it is known that the minimal volume is equal to that minimal volume that I define using a lower bound on the sectional curvature. And since the essential minimal volume is pinched between these two kinds of minimal volume, they're all equal. In dimension 3, they're then all identical. So these are the applications, and I'm going to end with just a general question. Most of the definitions that we use for minimal volume or essential minimal volume, they make sense when you replace the curvature condition by a lower bound on the Ricci curvature. For such a condition. And so you might ask, well, you can kind of essentialize, say, the minimal volume that corresponds to this condition, and you want to study this essential minimal volume. To essentialize the minimal volume where instead of a sectional curvature bound, you have a Ricci lower bound, for example. And you might ask, well, a lot of things make sense. You just replace lower bound on inrad by lower bound on one ball. Huh? And the conclusion is, okay, you can study such a thing, and I have no idea how to prove such properties, corresponding properties for this essential minimal volume. Such results for this essential minimal volume. And I have no idea. So we really need, for the sectional curvature, we really used in a strong sense all this theory of collapsing, and such theory is not available for lower bound on Ricci. I suspect that for this extension of the result of Besson-Courtois and Gallo, you could prove something like this for the essential minimal volume using Ricci lower bound, but it would be maybe a much more indirect proof, because you would clearly not have such a thing available for the Ricci lower bound case. So that's the end of my lecture, and it was very pleasant giving this lecture. So thank you very much for your attention.
Thank you very much, Antoine. Are there any questions? So I may have one. I mean, can you compute the central mean volume of a quotient, compact quotient of a complex hyperbolic manifold?
Oh yeah, that's a good question. So no, as you already mentioned in your papers, I think so the minimal volume itself is not known, and the essential minimal volume, I have no idea then how to compute it. So I would imagine if you want to start, you would start with the minimal volume. Yes.
Okay, so we are still stuck in this story.
Oh yeah. So this problem definitely. So there's this problem. A similar question is the minimal volume of the force sphere, say.
Yes, indeed. So for everybody, I recall that Antoine will be giving a lecture next week, and if I'm not mistaken, it's on Monday, 5:30 p.m. in Paris time. And so I take this opportunity to thank you very much for these beautiful lectures, and we appreciated all the examples that you gave, and and the correspondence between F structure and N structure is very interesting. I mean, I've never understood this very well, so I'm very happy. And so we thank you very much, and we'll see you next week.
Bye bye.
Merci encore.
Hein.